Welcome to the Bangalore Theory Seminar Series. This week we are very excited to have Chandrasekhar Mukherjee as our guest speaker. Chandrasekhar is a third-year PhD student at University of South California, where he works with Professor Jiapeng Zhang. He's currently exploring the area of unsupervised learning, random matrix theory, and random graph theory. He's interested in understanding the fundamental limits of clustering in probabilistic models as well as design practicable algorithms. Furthermore, he is also very interested in generative modeling of real-world datasets to gain further insights on them. Today, he has very kindly agreed to give a talk on his exciting recent work titled Detecting Hidden Communities by Power Iterations with Connections to Vanilla Spectral Algorithms. So let's welcome Chandrasekhar and all over to you.
Thank you, Ramesh. Thank you so much for having me and giving me the opportunity to present here. So without further ado, I'll just start and then you please stop me and ask me questions if you have any questions at any point. Cool. Okay. So as titled, this research is about finding hidden communities through the very well-known power iteration framework. And we'll also talk about some connections to vanilla spectral algorithms. Of course, I'll define what I mean by vanilla spectral algorithms, etc. But let me start. So first, let me give you some background and motivation. Right. So we are in this paper, we are mostly interested in the stochastic block model, or rather a particular version of it, perhaps the most popular version of it called the symmetric stochastic block model. So in this model, essentially you have a graph on n vertices, and there is k many hidden communities defined on the vertices such that for each pair of vertices, if they are in the same community, then there is an edge between them, added between them with probability p, and otherwise there is an edge added between them with probability q. So a graph is generated through this random process, stochastic process, and then the target is to, given this graph, find these hidden communities or clusters with high probability. And just some basic terminologies, we are going to use A to describe the adjacent symmetrics of the graph, and SI will be the size of the ith largest cluster. So S1 is the largest cluster, and SK is the smallest cluster because we are thinking there are k many clusters. And sometimes I'll also use S star to denote the largest cluster. So S1 and S star interchangeably, and then so on. So in general, this problem can be defined in three settings based on the values of P and Q. So if you have P and Q to be A over N and B over N, that means the number of both intracluster and intercluster edges for any particular vertex is just constant number of edges, then this is called the linear degree paradigm. And if the average degree of the graph is logarithmic, which means that so we are assuming that P and Q are A log N and B log N over N, and that's called the logarithmic degree regime or paradigm. And whenever we are dealing with P and Q, both are larger than log N of N, it is called the dense graph regime. So we'll just focus on the dense graph regime today. And the reason I make this differentiation is that the techniques used or the problems of interest used generally change from one regime to another. For example, in the first case, you are more interested in weak recovery. In the second case, probably the most interesting problem now is understanding something called the case threshold. But in the dense graph regime, there are some other interesting problems that we'll talk about. Right. So the primary motivation of our investigation of this problem was essentially the observation that in stochastic block model, there are several algorithms that achieve very good guarantees, in the sense that for example, in the logarithmic degree case, there are polynomial time algorithms that achieve the information theoretic bound, and so on. But one thing we observed that in a lot of the cases, these optimal algorithms, so to speak, require a lot of extra artificial steps, if you will say so, in the sense that you would not expect these steps to be required to solve this problem or find these clusters, but for the sake of proving some guarantees, sometimes we need some extra steps. And in contrast, we see often that in practice, a lot of the most popular algorithms are perhaps the simplest algorithms. And this definitely holds true for clustering algorithms, such as a lot of the times, for example, this is a bit tangential, but like there is an algorithm called Lovan that has been used extensively in many different problems in many different areas. And it's just like a very simple greedy algorithm. And as we will show, that there are some very simple spectral algorithms, such as PCA, that have been really shown to be powerful in practice. And so makes it interesting to study the power of just simple algorithms, even in theory. And in fact, this has been the study of several papers before, as I mentioned here. And the study of very simple spectral algorithms, again, such as PCA, is called the study of vanilla spectral algorithms. Similarly, another observation we have had is that when the setting is more heterogeneous, sometimes proving optimality or performance of algorithms can be harder. For example, one of the settings of stochastic block model is that when there are a lot of very small irrecoverable clusters, coexisting with some large recoverable cluster. I will go into detail about what I mean by recoverable or irrecoverable, but it turns out when there are a lot of small clusters in the graph, it becomes hard to argue that there exists an algorithm that provably even recovers the large clusters. And in fact, in this setting, all the algorithms that have been able to recover these large clusters they always required the knowledge of the probability parameters P and Q. So if you recall, P and Q are the intra-cluster and intra-cluster probability, intra-cluster and intra-cluster probability that was which was like given to which was used to generate the graph. Now we would expect to not need these probability parameters, and in fact, in the other setting where all the clusters are large, we indeed do not need any such parameters. So these are the two main problems that we are interested in to. So let me first talk about the small cluster barrier, then I'll talk about the vanilla spectral algorithm, and then we'll talk about our contribution. So the small cluster barrier in is the phenomenon that the theoretical guarantees of most SBM recovery algorithms require all clusters to be large, such as omega square root n. So as you would expect, and of course there is some dependencies on P and Q, but I'm omitting it for now. So you can say omega P comma Q square root n. So on one hand, if all the clusters are little o of square root n, then it seems unlikely that a polynomial time algorithm exists that can recover these clusters, if you even consider P and Q to be constant. So the idea generally is that like P and Q are like the size of the recoverable cluster is inversely proportional to P and Q. So the smaller P and Q get, the larger becomes the minimum size of the recoverable cluster. For example, if P and Q are something such as A over N and B over N, you can probably only cluster something like a constant N size cluster. Okay. So the question then is that, okay, so if all clusters are larger than all clusters are omega square root n, then there exists a lot of algorithms that are able to recover these clusters. On the other hand, if all clusters are little of square root n, then it is unlikely that an efficient algorithm exists. So what happens in the middle ground? That you have a lot of large clusters as well as a lot of small clusters. So you may have the following setting that you have the first cluster, let's call it V1, its size is N2, and then you have V2 until Vn over 2 minus 1. All of them are just singleton clusters. So you may have the situation that there's one large clusters and a lot of singleton clusters, which you may even think about just random nodes in that graph. In such a setting, you would expect to recover that large cluster, but it seems quite hard to show that existing algorithms are able to recover this large cluster. And in this direction, to the best of our knowledge, the state of the art until last year was this result by two papers. And it showed that they are able to recover square root n log n with some additional terms on the factors on the probabilities, as long as the size of the largest cluster is log n squared times the size of the second largest cluster. So essentially, they had a gap constraint. So they could only recover a large cluster in this unbalanced SBM setting or the small cluster barrier setting, where the size of the largest cluster is at least log n squared times the size of the second largest cluster. And in some particular settings, such as if they assume that k is less than log n, they were able to reduce this gap constant to like a constant factor, but they still needed this gap constant. And on top of that, okay, let me first continue this. And later, we showed that you can indeed design an algorithm that does not need this gap constraint and does not also need any dependence on k to remove this gap constraint. So we were able to show that you can just recover as long as the size of the cluster is larger than square root n log n. And after our this previous result, there has also been a result just published in the last few months that also show the same thing, of course, but albeit with a different algorithm. So we use a very famous spectral algorithm by Van Wu and build on it to show that you can cluster in the unbalanced setting, and the other paper does this in using an SDB relaxation algorithm. However, all the algorithms that I've talked about so far, they all, again, require the knowledge of P and Q, which is quite restrictive as far as clustering in stochastic block model goes. And also we observed and tried to analyze whether you can estimate this P and Q in the graph and see if you can do something with it. But it turns out that it is also hard because of the fact that these algorithms are quite sensitive to these parameters. So if you, instead of P and Q, if you have P plus epsilon and Q minus delta, you do not know the behavior of the algorithm, and it's hard to quantify. In this direction, in this paper, we show that we can design an algorithm that does not need parameter knowledge and is able to recover the largest cluster, as long as the size of the largest cluster is square root n log n power 5. So this is, you can say, suboptimality we have here compared to the state of the art, as well as a significantly weaker gap constraint is that we require the size of the smallest cluster to be at least log n squared times smaller than the size of the largest cluster, as compared to, let's say, the size of clusters, there being a gap between consecutive sizes, as was in the case. Yes, Anand, please. Yes.
So is there a easy way to estimate P and Q? What you mentioned the previous slide, P plus epsilon, Q minus delta, that kind of an estimate?
Right. So when you say like easy way to estimate, I mean, of course you can make some estimates. Now it is hard to get, like, the problem is then what error are you able to deal with? For example, I could give you the following, that let's say for any vertex V, I calculate the degree of V. And let's say V belongs to the cluster whose size is Si. Then the degree of V divided by N, for example, will be of the following form: Q plus P minus Q Si over N. So you can get like something like this. So if you just calculate the degree of the vertices, you get an estimation of this form. Now the error term here is this.
Of SI as well, right?
Yeah, but the point is that you do not need the knowledge. My point is that if you just calculate the degree of a vertex, then doesn't matter what SI is, like whatever SI is, let's say V belongs to, like, this vertex V belongs to VI. So the resultant estimation will be of the form this. So you do not know VI, that's why depending on the degree of different vertices, it gives you different estimations to the Q probability parameter, which is the intercluster parameter.
Oh, okay. I guess you're saying that if the cardinality of VI is small, then the P minus Q cardinality VI divided by N, that would be the error. Is that what
that would be the error? Exactly. So in our case, as long as now make this observation here, that in our case we just need S1 larger than Sk log n squared. So as long as this Vi is smaller than like V1 over log n squared, we are able to survive that amount of estimation. This is what essentially also that our algorithm is designed in such a way that you are able to deal with, you are able to essentially deal with a heavy error, if I may say so. But if you apply this to the existing algorithms, it's hard to analyze what happens. In fact, we could not analyze. We tried for like significant time, but we are not able to.
Okay, and the second question is, does this theorem and the previous ones require the knowledge of S1, or you don't need that?
No, we do not need knowledge of S1. So that's actually a very good question. So in our case, so in the previous algorithms, if you know P and Q, you can estimate S1 very easy. you just essentially do a lot of neighborhood calculation, and then that helps you get a very good estimation on S1 because you know P and Q. In our case, we do not need the knowledge of S1, but the hardness, the problem with that, like we have a subtle problem in the sense that it's hard to say when the algorithm succeeds or fails. So we show that if indeed S1 exists and S1 has a large value, then we are able to recover.
Okay.
But on the other hand, if there does not exist any S1, then our algorithm will not say, oh, you cannot recover.
Okay, thank you.
Right. And before I start talking about our algorithm analysis, one second. Before I talk about our analysis, now let me also motivate the problem with vanilla spectral algorithms. So vanilla spectral algorithms, like I said, is kind of the idea, or it's a long-held expectation that at least in the stochastic block model, just a very simple spectral algorithm should be able to recover things as well as the state of the art. And this has been an area of research in the last, somewhat active area of research in the last 20 years. So let me first tell you some candidate vanilla spectral algorithms, and then I'll tell you what are the problems in proving that they're indeed good or what progress we have. So this is the first one. So we call this the SVD1 algorithm. So essentially what you're doing is, let's say you have the adjacency matrix of the graph. You are just taking the first k eigenvectors of that graph and then projecting the matrix onto the span of this first k eigenvectors. And you then are getting an n cross k matrix. So here you are assuming that you know the value of k. So here you are getting an n cross k matrix. And essentially you are arguing that if the graph is indeed, the SBM graph is indeed clusterable, then in this post-projection matrix, the vertices belong, the columns corresponding to intra-cluster vertices are going to be, the distance between them is going to be 1/4 of the distance between intercluster columns. So essentially you are able to obtain a geometric separation. So it's like you just apply SVD and then you say, okay, after this SVD, the columns of vertices from the same cluster are going to be very close and columns of vertices from different cluster are going to be far away. And that's as simple as this algorithm is. Okay, so this is a candidate vanilla spectral algorithm. Another candidate vanilla spectral algorithm is you look into the individual entries of the first k eigenvectors and then you make some like simple, let's say threshold based calculation to choose divide the graph into different clusters. In this case, there has been a very nice result by Abe and the other co-authors in 2020, who showed that a very simple vanilla spectral algorithm for the case of only 2 clusters. So they showed essentially just given this graph, you just take the eigenvector of second eigenvector of the adjacency matrix, and you just look at the values of this eigenvector. So you get an n dimensional vector. So whichever value is larger than 0, you put it into one cluster, and whichever value is smaller than 0, you put it into other cluster. And in fact, they showed that in the logarithmic degree setting, this algorithm is as good as the state of the art, even I think as far as I remember, information theoretically correct. And this is a very nice result. But the problem with this result is that they are not able to extend this for the case of k greater than or equals to 3. And they also make some arguments that why that is the case. And it seems hard to just extend their analysis and method to larger value. On the other hand, there had been another result that also had like a similar entry-wise vanilla spectral algorithm for a constant k. It was not as tight as Abe's result for k equals to 2, but it was still a good result, I think, up to some logarithmic factors. But again, you cannot extend this result for larger k. For example, when k equals to little omega of 1 or little omega of log n, whenever k is equals to little omega of log n, there is no way to extend these algorithms. So in the case of large k, where let's say k is much larger than log n, there is the most vanilla spectral algorithm is the one that I'm showing here. So if you remember, I said that the vanilla SVD algorithm does the following. It just takes the eigenvectors of the first eigenvectors of the adjacency matrix and projects the adjacency matrix onto these eigenvectors. In this case, you randomly divide the columns of the matrix into 2 halves. you get the singular vectors, because now the matrix is not symmetric, so you don't have eigenvectors. You take the singular vectors of the left half of the matrix and project the right half of the matrix onto this left half, or onto the eigenvectors of the left half. So you divide the matrix into two halves, you calculate the eigenvectors of the left half and project the right half onto the eigenvectors of the left half. And then you show that the eigen and the columns in the right half, which you projected now, are now separable post this projection. So this is the idea, and this is the SVD2 algorithm that I also said that we previously used to prove an unbalanced SVM result, despite while using the parameters. But anyway, in this case, so the main difference between the vanilla spectral algorithm and this is that they are not projecting onto the eigenvectors that they're getting from the same matrix. So there is a partition before projection step. And indeed, this step seems artificial, and it was noted by Wu. So he said that SVD1 algorithm seems very natural and one that people would use in practice. And in fact, it is very close to the PC algorithm that people use for dimensionality reduction. And it's also known to have some noise removal that helps in clustering, etc. But it seems it's hard to analyze. And that's why they analyze this slightly more technical SVD2. So the main technical difference between analysis of SVD1 and SVD2 is that the entries of the eigenvectors and the entries of the matrix in SVD1 can be arbitrarily correlated. But if you break it into two halves, then there is no more correlation. And as it is well known that if n is large enough, then if you are taking n over 2, the eigenvectors of the left up and the eigenvectors, the singular vectors of the left up and the eigenvectors of the whole matrix would basically be similar, and they would like occupy the same subspace. So that's the idea they use to solve this problem. So the problem here, the technical problem here to proving vanilla spectral algorithm is this correlation value. So in this direction, we show that a centered version of SVD1 geometrically separates the communities in the balanced case. So we can show it to an almost balanced case, but for this problem, we make the assumption that there are a lot of clusters and all of them are of the same size. In this setting, we show that SVD1 is indeed able to recover. So we achieve both of these results using a power iteration framework that now I will talk about. So just let me very shortly recap the problems of interest we have. So on one hand, we are trying to show that you can do better than before in the unbalanced SVM setting where the size of clusters are very different. On the other hand, we are using the same techniques to show that we are able to sorry, actually, there is a small error. It should not be when facing the small cluster barrier. It should be when facing the normal problems. In the balanced case, we show that a simple PCA-like projection suffices. And on the other hand, we show in the unbalanced case, you can recover in a parameter-free fashion. So let me now describe our power method algorithm. So the algorithm is very simple. So actually, what I will do is I'll first define our algorithm and also describe the analysis by assuming that I know the knowledge of Q. And then, as I said before, essentially in our case, we can replace Q with this estimation, which is the minimum degree of the vertices. And as long as there is a size gap between the largest and the smallest cluster, our analysis goes through very simply. And then we are, again, we are able, that is how we are able to get our parameter-free result. In fact, when we wrote our algorithm, we did not know that there did not exist a parameter-free algorithm in unbalanced SVM. So that was quite nice when we indeed we actually realized it after we had submitted our paper. Anyway. So yeah, let me now define our power method algorithm. So we have the graph with the parameters. We just need Q for here. And we have a threshold delta. And also R is some parameters. We will explain how to choose them. Essentially, you can think R is equals to log n for all intents and purposes. So what we do is we first shift the matrix by subtracting each entry with Q. And then we just take a log nth power of this matrix. And after that, we just separate the clusters based on this threshold. In the sense that if after this projection, if two columns have distance less than delta, then we put them together. So what we are able to show is as follows. So we are in the dense graph regime. And let's say there is a size of the S star is the size of the cluster, the maximum largest cluster, and we have this fact that there is a log n to the power 7 in our case, as opposed to a log n in general result, which is within polylogarithmic factor. And with probability 1 minus 1 over n, one of these separated sets will be the largest cluster, that clean largest cluster. And in fact, we can also easily identify which one is that cluster, given the fact that indeed S1 is larger than log n to the power 7, square root n log n to the power 7. So let me briefly just talk about this algorithm one more time before I talk about our analysis. Actually, before I talk about analysis, first I will show you how this gives us the unbalanced SVM algorithm, and also give you the connection between this and Venn-less spectral algorithms, which actually is quite simple in the balanced case. So again, the entirety of the algorithm is that you just shift the matrix, shift the entries of A by Q, and then take a log nth power of the matrix. And then the columns of the matrix, you can think that they are now geometrically separable, or the largest cluster is geometrically separable. Of course, you may have a lot of very small clusters that you cannot separate, but we do not worry about that. You can just separate the largest cluster. And in that case, you can keep filtering as long as there is a cluster that you can recover. So the parameter-free version is obtained very simply. So as you might have noticed that we have two parameters, delta and Q, the intercluster probability parameter, and delta is the threshold which we are using to separate post-projection, or rather, sorry, post-powering. So delta you can just simply choose to be something as like 1/4 of the maximum distance in B to the power R between two columns, and that suffices. On the other hand, for Q, we replace Q by the minimum degree of the vertices in that graph divided by n. And it is very easy to see that the value of this, let's call this the Q hat. So Q hat is approximately going to be of this value. So Q plus P minus QSK over n plus some lower order terms. And we are able to show as long as S1 is larger than SK log n square, our algorithm works. I'll also give you some intuition why we need this. And in fact, we do feel that this gap constraint we should be able to remove this gap constraint, and that is one of the future directions that we are trying to understand now. And as I have said, there's a cost to making this algorithm parameter free. Essentially, we need a gap constraint, and we also have this log n power 7 bound in the recoverability as opposed to just log n. So one small thing here is that, yes, I am using the minimum degree as an estimator of Q, but you can think a more natural estimator may be the fact that I can just do a centering of the matrix. So given A, I can calculate the column mean for each column, and then I get a vector, and let's call this vector C. So then I subtract each row of A with like C. So essentially what I do is AI, which is the ith, let's say, row, is equals to AI minus C. So I'm just doing a centering step, and the centering step is essentially what is used in, for example, PCA. Now, we expect that this may also suffice, and again, this is a more natural centering step, but there are still like some remaining barriers in the theoretical analysis that stop us from using this step. Instead, we take that minimum degree and we say that as long as there is a gap between the size of the largest and smallest, we are able to recover. Okay, so before I go to the next part, if you have any questions, please ask me. Yes, Anand.
Yes, so does this not work when, let's
Sorry,
say,
I can't hear you. 1 second, my bad. Yes, can you please repeat?
Right, so if all the clusters are of the same size, then we would not be satisfying this constraint, right?
Right. Yeah. So that's a very good point. So it's essentially a bit dichotomous. On the other hand, if size of all the clusters are same, then actually it's easier to like you can use the degree of you can take any degree and divide by n, and the analysis will work. So we are kind of stuck between these two situations. So if everything is very balanced, then our method works. In that case, you do not even need minimum degree. You can just use any degree and it'll all work. because as you are saying, all these values are very similar. On the other hand, if it is very unbalanced, then yeah, you need this gap. But so essentially we are left with this situation where what happens when the minimum is closer to log n, but not quite close.
So is this gap, the role of this gap is to get an estimate of Q, is it?
Yes, exactly.
Okay.
So
Okay.
I will tell you exactly where it comes into play.
Okay, thank you.
Cool. So before that, let me just tell you the connections to SVD. And I think like it might be a little obvious, the connection between powering a matrix and its eigenvectors. I mean, we know that like if you power a matrix, like if you take a random vector and power it a multiple times and multiply it with the multiple times with the same matrix, then you get the first eigenvector. So essentially, it's just a consequence of that. So now we are talking about the balanced case. And in the balanced case, instead of taking the minimum degree, I am just taking the average degree and then dividing it by n. So here I must note that essentially any degree of Vi over n works. The reason I am setting, so you may think that in this case PCA works, right? Because if any degree works, I can, and essentially when you think about the centering part, essentially centering in the PCA sense is nothing but subtracting with the degree of each vertex, like the average degree of each vertex. Sorry, the degree divided by n for each of the rows. So if indeed choosing any degree divided by n works, then we should be able to do PCA here. But the only problem we have here is that we are making some calculations and assumptions that require the matrix to be symmetric. If you do a PCA-like projection, then the resultant matrix is not symmetric anymore, and that causes us to like not be able to completely get the tight result. So that is also, again, in the same way, it's an interesting result. So we would like to show that you just take a PCA centering and it works both in the unbalanced and the balanced setting. So now let me tell you how the connection between the power matrix and the projections eigen projection is like established. So remember that for any k prime, this is the projection matrix for the first k prime eigenvectors of B hat. So we can write it down like this, where Pj are the eigenvectors of B hat, which is our centered matrix. Right? So you can just, for any column, pk prime B hat U can be written down as the sum of the projections onto the first k prime eigenvector. On the other hand, the ith column of B hat power r plus 1 can be written down in the same fashion, because you just essentially you write down B hat as any column of B hat as a sum of its as a decomposition onto the eigen. You just do an eigen decomposition essentially and then power it with B hat a lot of times, and this is what you get. So because we are working in the balanced model, what we have is that lambda 1 same as lambda 2 up to lambda k, and lambda k plus 1 is quite smaller than lambda k. So that means in this calculation, essentially you can write that this is equals to j equals to 1 to k some lambda power r pj comma u pj plus epsilon. And this happens because of the fact that lambda k plus 1 is much smaller than lambda k, and this is a result of the fact that the matrix is balanced. Because the clusters are same size, so it's the balanced SVM model. So because the size of the clusters are same, the eigenvalues are also going to be quite similar. And then there is an eigengap. So because of that, now you can see that this and this part is very similar up to this lambda r, and then you can treat this essentially just as noise. And we show that this noise is not going to cause any problems. So that kind of gives us our algorithm. So our algorithm is nothing that but the following. So we just take the average degree of the graph, and we subtract it, normalize it by dividing by n, and subtract it to b, and then we take the first k minus 1 projection operator and then just geometrically separate it. So that's our centered SVD algorithm. And for the balanced case, so we just take the average degree, and then I can just take the first k minus one left singular vector, essentially the left eigenvectors, because the matrix remains symmetric, and we just get the final result by geometrically separating it. By whenever I say geometrically separated, I means that you can show that each the maximum distance between intra-cluster columns is less than 1/4 of the minimum distance between inter-cluster columns, and such a setting is sufficient to recover. Yeah. So this is the results we have in terms of our final outcomes. So as I told you, we showed a very simple power method based algorithm to recover unbalanced clusters in a parameter free sense, due to the fact that the parameters initially needed in our algorithm are quite robust to estimation. And then I also showed that using the similar technique, I am able to show that a centered SVD is optimal up to, again, this logarithmic factor. We have like a huge number of log factors. So since the publication of the paper, we have been able to reduce it to something like power 8 now. And in the previous case, instead of log n power 7, we have something like log n power 4 now. But I think it's still an interesting and hard challenge to even remove the log factors. Not so much because it improves the bound so much, but we feel that it presents some different technical challenges that needs to be overcome. So these are my results. Now, in the remaining time, I will talk about our techniques and how we go about analyzing it, which is we essentially create a certain random partition method to analyze the entries of eigenvectors that we hope that is going to be quite interesting, and maybe we'll be also able to apply it to different random matrix theoretic problems. Okay. So again, so yeah, before I proceed to the final part of my talk, if you have any questions, please ask. Cool. Okay. Then let me tell you the layout of our analysis. Right. So the majority of the analysis is going to be able to just try to show that the columns of B to the power R is separable with respect to these underlying clusters, right? Okay. So now let me show you this explanation that we have this A B. So now I am going to assume that B is A minus this Q matrix, right? To make calculations simple. So now L is, so I'm dividing it into two halves, L and R, for the purpose of our analysis, where L is the expected value of B and R is the remaining noise. So here, for each intra-cluster entry of L, we'll have value P minus Q, and all inter-cluster values entries of B will be 0. This is because of the fact that if you think about expectation A, so because we are adding an edge between all intra-cluster pairs with probability P, the expectation A will, and you can think maybe like this is the view, like the first cluster, this is the second cluster, and so on. So then in expectation of A, these values will be P and these values will be, sorry, my bad. These values will be P, and then these values will all here be Q. So now because you are subtracting with Q, you are getting 0 here and P minus Q. And the primary benefit of that is, while if you think about just L to the power R, the intercluster entries will continue to remain 0, but the intracluster entries will become much larger, something such as P to the power Q minus R times, let's say this is the second cluster, right? So S2 power R. So it will be different for each cluster. But essentially what is happening is that because you are centering the matrix with Q, when you are taking the power of this matrix, the intra-cluster values are going to essentially rise with the powers, and the inter-cluster values will not get affected. And essentially proving the whole part of the problem is the fact that when you are looking at B to the power R is dominated by L to the power R. Because if you are able to show that, then we are done. And on the other hand, think about this, that let me actually go here. So now we have said that B equals to L plus R. So L, we understand very well that it preserves the block structure. Now R is a zero mean random matrix. So our essential calculation when we are dealing with B to the power R is going to be as follows. So we are going to do a two-step breakdown. So as you can see, B to the power R, I can write it down as L to the L plus R, capital power R. So let me just call this log n so that we don't mistake, and let me call this T. Right. So what is happening is that I'm just like unfolding it one at a time until like so. So this is of course we can expand it as this is power of two variables. You can think L and R as two variables now. So then I just write it down in the following that L to the power T minus 1R and then L to the power T minus 1, T minus 2 RB and so on. So I'm basically breaking it until I see the first instance of R in my expansion. So this term is called M. And essentially what we are going to do here is we are going to show that L to the power T minus, let's say, something like L to the power T minus A minus 1 R B to the power A, something like this. So these are these terms, right? So when I'm calculating the term, I'm going to calculate the maximum row norm of this. So basically, I'll just say the maximum norm of the row of these terms are going to be very small. And this is quite easy to show because it comes down to this norm of this multiplied, sorry, row norm of this, and then multiplied by the norm of B to the power A. We can upper bound B using simple random matrix theoretic techniques. And here it's easy because you are multiplying this very well-defined matrix with a random matrix. So you can just use Chernoff bound to get very good estimates on this, tight estimates on this, and then it suffices. So this part is quite easy to deal with. M. Okay, so if you have any questions again, I'll just stop for a second. Please also let me know if I'm not making sense in any part of this. Cool. So, okay. So the first part is easy. So again, just to recap, I'm starting with B to the power R. I'm breaking it down into its expectation and the rest of the random matrix part for my analysis. I know that the expectation part is going to, if I can preserve that L to the power R, I am done. So I'm breaking it down in two cents. And the first things I'm able to show that this part is quite easy to analyze using just nothing more than Chernoff bound and some upper bound on spectral norms of random matrix. Now this part is left here. Now this part is the harder part in our analysis, and this is you can think this is the main technical contribution we have. Is as follows. So now I'm breaking it down again in the same way until I'm left with this R to the power R term, which is you can think about this as pure noise. So the challenge of our problem is to how to well analyze something like R to the power L rho norm. So previously, if you look at like analogously, we were trying to analyze something like this in this part. So this part is easy because L is very well defined. This simple Chernoff bound because linear combination, each entry is a linear combination of this R and L, and then you are done. But this part, because you're taking the power of R, if you try to do it naively, then you will end up showing that there is no difference between just like we want to show that this is smaller than something like this, right? So this is what we want to show. So we want to show that there is indeed some cancellation, if you will, that is happening when the matrices are getting power. Yeah. So as the degree R increases, the effect of R to the power R on B to the power R decreases, and then it vanishes. So we are left with this M prime. So just to recap, we had B to the power R is equals to L plus R power R is equals to terms such as And this part is easy to analyze. And then we are left with, if you will, the harder part of something like R square L, B, R minus 3, these kind of terms. And then we are also left with R to the power R. This one is again easy to analyze just using spectral norm arguments. And then we are just left with analyzing these kind of terms. Because essentially what we will do is, for analyzing this kind of terms, we'll analyze this and then just use a naive bound of spectral norm on this. So let me just give you a high level argument of what we are trying to prove, or how we are trying to do it. So R to the power L, let's say I'm trying to analyze, we're trying to analyze the A comma Bth entry of it. So you can write it down as a sum of T degree monomials, right? T term monomials on this R matrix, because you can think about it same as doing all possible, taking all possible paths between the vertices of a graph in the same sense. Sorry, you taking like paths of a particular T distance between two vertices, all possible paths. And so we have this sum of product setting, and there is a lot of correlation between different product terms, which you can think is the hard part of the analysis, or which is what like gives the hardness to the analysis. So we have essentially n to the power t many terms, and there is a lot of course, there are similar terms up to permutations and such, but also there is a lot of terms with arbitrary correlation. So let me see if I should go to details. But first, let me tell you this. Essentially, what we are trying to do here is, so we have a sum of product. I'm going to convert it into a product of sum via a random partition argument. In fact, I kind of now feel the proof, like this part is like, in essence, similar to how we learned how to prove Hasted switching lemma, for example, where you are converting a DNF to CNF and CNF to DNF in alternative round. Here we are continuously converting a sum of product to product of sums using a random partition. So I'll tell you what random partition is. It is in some sense similar to random restriction, but of course, very different problems and applications. But we felt that there is this nice, at least visual connection. So let me see if I have the time to explain. I have 10 minutes, so I'll try to keep it short. Okay, let me just try to explain this term, and let me tell you how we are going from a sum of product to product of sum. Cool. So as I have said, we are dealing with this following situation. RAL1, we are trying to analyze this following thing. LTB, and then this L1 to LT. Now, assume the case where, or just the cases where L1 not equals to L2, not equals to L3, not equals to LT. So we are considering the, oh sorry, this should be LT minus 1, but simple. So we are considering the sums, we're considering the monomials where all the indices are different. Now, of course, there is still going to be, if you consider the sum of these monomials will still have a lot of correlations between them, but at least they are not same. They're unique. So this is essentially, you can think about this is also like same as a self-avoiding walk on a graph. So we're just considering those terms. So basically, I'll consider these terms and show how I can convert this part into a product of sum. And essentially, the similar argument applies to different arrangements and of uniqueness between these indices. So I'll just make sure that I'm on the same page with you. So again, what I'm trying to say is that I'm trying to analyze R to the power T L A B, which is nothing but the sum of all monomials of this form. So these are just an T long walk. And this L1 to LT can be anything in the N. And now I'm considering the particular setting. And now I'm saying that I'm going to convert this sum of product into a product of sum. And I'm going to consider the particular setting where L1 not equals to L2 not equals to L2. So I'm considering you, if you will, the self-avoiding walk setting. And what I am doing here is that I am doing a random partition. That is, I am given given 1 to n, I'm going to partition them into some log n many sets, t1 to t log n. I'm going to partition them into some sets. And then I'm going to consider this even smaller subcase of indices where these indices are disjoint. That is, I'm going to consider all the summations where of this form such that L1 belongs to T1, L2 belongs to T2, and LT belongs to T. So essentially what I'm doing is, instead of calculating the sum of all the monomials of all the distinct monomials, let's say self-avoiding walk monomials, I'm only going to consider a random subset of them such that all of the L1 belongs to a different partition, all of the L2 belongs to a different partition, and so on. And basically we are going to show that whatever this value of ST is, this is kind of, you can get like, you can multiply a log n power log n, something like this, to this one, and you will go back to this particular setting. So I'm starting with this setting, and then I'm applying a random partition. And then I am saying that after that random partition, I have a smaller subset of monomials. Now I am able to analyze them easier. And I'm saying that with very high probability, whatever the value of these monomials, this particular subset of monomial is, it is going to be within a log n power log n factor, or 1 over log n power log n factor of the all these self-avoiding walk monomials. And we like require a few steps of this. And in each of these kind of steps, we are kind of, you can think we are acquiring an extra log n factor. And that's what gives us a log n power 7. So to kind of summarize, we start with the sum of product. Now we are just looking at the self-avoiding walk sum of product, which is the L1 not equals to L2 not equals to LT, RA L1, RL1 L2, RLTB. And then I am looking at even a smaller subset of them through a random partition such that L1 belongs to T1 and LT belongs to TT, and then again R A L1, R L1 L2, LT B. And the final step kind of idea here is that once you have this setting, because you have assumed that there is these indices are going to be different, you can convert this monomial into this setting. So because these are all different, you can bring the sum symbol from out here to here. And now this becomes a product of these two things. And this is nothing but a linear sum of these random variables, and you can calculate it. And once you calculate it, you can now keep doing it backwards. So every time you are calculating it, then again, you can bring another sum symbol to the front and then keep calculating. And if you are like, we are assuming that there is a high enough probability that this happens, then with simple union, sorry, actually after this, if you try to make this argument for all things using union bound, you have some problems. So instead we use a higher moment method to finish off things. But the essential idea is the same, like what I said. You start with sum of products, you look at a particular set of sum of products, and then you take a random partition on the indices. So you are now looking at even a smaller subset, which is still not significantly smaller. However, once you have taken this random partition-based subset, you are now able to do a recursive transformation from a sum of product to a product of sum, and thereby calculating using again Chernoff bound in each of these rounds. And that's how we essentially analyze this R to the power TL kind of terms. To give you a very small essence of what we are proving is that using this technique, if you, and L is essentially, you can think about this technique works even when there is no L, as long as there is just you are analyzing random like entries of random matrix. So let's say R is a zero mean random matrix. And let's say its variance is something like sigma. So for any large R to the power R, so norm of R to the power R is going to be something like sigma square root n power R. And you would expect that infinity is something like sigma square root n power R over n, something like this. In our case, using this technique, you would be able to prove that this is log n power 7. So this is essentially what we are able to achieve in like a example sense. But of course, our application is more to the analysis of R to the power TL, and to the best of our knowledge, it was not possible to, like, we didn't know how to analyze this kind of matrices before. So I will now close my presentation here with some future directions. So in the whole analysis, we talked about stochastic block model, where there were only two probability parameters, P and Q. So we're interested to understand what happens when there are multiple probability values. And like I mentioned a few times, that we would like to change our partition centering processes to PCA. And also we would like to see the application of low degree polynomial in other setting. So one small thing is, like I told you, like our analysis essentially starts by observing self-avoiding walks. So self-avoiding walks themselves are quite interesting, and they have a lot of application in many different areas, and even stochastic block model. So if our method can be used to analyze this self-avoiding walks in different problems is also an interesting direction. Thank you.
Okay, so let's thank the speaker for the talk, and can have a few questions.
So in this analysis, I guess you would want to show concentration at every step, right? How does
Right.
show those things?
Yeah, so at every step, so your question is that how are we showing concentration at every step?
Yes, yeah.
Right. So here, let's look at this setting. We'll look at the first step. So here, this value is going to be something as square root P square root S log n, right? Because of the fact that, think about this, that this is just a multiplication of a row of R with a column of L.
Okay, so I guess
Now,
here you can share or something, right?
Right, yeah. So once we have done this, so now we can look at this. Now these with very high probability. So essentially what I'm going to show is, instead of log n, I'm going to show log n square. I'm going to make an assumption. I'm going to prove it with probability, like I'm going to take this bound. So now I'm able to prove, like say that this happens with probability 1 minus, such as log n power log n, right? Sorry, my bad, n power log. So this happens with probability 1 minus n to the power log. So in the second case, now this is again a random variable, but with very high probability, we know its radius, because before it was a 0, 1 random variable, but now it is a random variable of radius square root P square root S log n. And now when we are multiplying this, so this is again just a random variable of this. And now this is now then going to give you square root P square root S, sorry, log n to the square, log n square, then again multiplied by square root P square root n log n square. So because now this is just, again, a Chernoff bound with just a radius.
Oh,
so
okay,
I can continue to do this.
Right, so lengths of your paths are also log n, so I guess.
Yes, that's why this works, exactly. If you and this is in fact like the problem occurs whenever if you try to look for larger than log n power, then this will not, again, like we will not be able to prove things.
And what about the first step when you're doing this random partitioning?
So yeah, so the random partition is, again, we are dividing things into, like we are taking we have n. So we are dividing n into some log n many partitions. So then for any particular monomial to be present, is that the probability of that is going to be 1 over log n power log n. So with probability 1 over log n power log n, any of the monomials that was there in my is self-avoiding work like sum will still remain in my random partition. And that's why it means that if I can bound whatever I bound here, if I'm bounding the absolute value of this, so I can get multiply by log n power log n and I'll get it. And now essentially what I'm doing is, because log n is essentially again r, which was my walk length, so I'm pushing one of the log n, like this log n, into my bound essentially.
Okay.
Yes.
Okay, yeah, thank you.
Cool.
Do we have any other questions? Okay. Yeah. Thanks for the talk. Very exciting results, Chandra. I'll stop the recording
Thank you,
now.
Ramesh. Sure. Thank you so much for having me.